Alright, testing. 1, 2, 3, testing. Let's see if this is working. Some good math practice that I need to. So I find that practicing math, one of the easiest ways to get better at math is just to learn about math history. So that's why I'm making this live stream right now. So I find that practicing math. Alright. Okay. Alright, let's roll with it. Complex plane is so important for our human technology. So I just think it's so interesting too. So let's see how much we can learn, how much we can practice of this math.
Up until elementary algebra and trigonometry, most individuals are not exposed to anything but real numbers. Then, when trying to find if an algebraic equation has rational roots, one stumbles upon complex numbers. Though not studied nearly as intensely as real numbers within the standard curriculum, these numbers are an essential part of mathematics, with a whole branch of mathematical analysis being dedicated to them, called complex analysis. The applications are far and wide, with the prime examples being in areas of physics, such as dealing with electricity. Despite how fundamental they are, it took until about the 19th century for imaginary quantities to be recognized as truly useful. Why did it take so long for mathematicians of the past to recognize the value of complex numbers? Why was it only 200 some odd years ago that the complex plane, which applies a proper geometric construction of complex numbers, was invented? The prospect of a negative within a square root was baffling to mathematicians for many years. They considered it to be an impossibility. It wasn't until the 16th century that any term was given to the square root of -1, più di meno, which literally translates to more or less. It was coined by Raphael Bombelli, an Italian mathematician who was the first person to really write anything remotely formal on the square root of -1. Alas, the name didn't stick, and in the 17th century, the square root of -1 gained a term that would actually stick: imaginary. This one was coined by René Descartes, a 17th century French-born mathematician, philosopher, and scientist, most notable for being the father of modern philosophy and making fundamental contributions to foundational geometry. He introduced this term in 1637 in La Géométrie, which was the fundamental work that gave birth to analytic geometry. In the 18th century, Leonhard Euler, a Swiss mathematician considered by many to be the most prolific mathematician to ever exist, coined I for the square root of -1 in a 1770 paper, roughly translated to, on differential, angular, most irrational, which is logarithms and circular arcs can be integrated. And in the 19th century, Carl Friedrich Gauss, a German mathematician whose contributions to mathematics gained him the title, the greatest mathematician since antiquity, coined the term complex number for imaginaries in an 1831 paper. There was great perplexity at and avoidance of negative numbers for a long time, too, as many couldn't conceive of the prospect of a quantity being less than nothing. Yet another reason that compounds why it took so long for people to accept the square root of -1. Before we actually dive in, let's give some insight into what a complex number actually is. A complex number is an ordered pair of any real numbers, let's say x and y, represented in the form x plus iy, where I equals the square root of -1. For ease, we'll set this complex number equal to z, so z equals x plus iy. We call x the real part of z, and y the imaginary part of z. Now, taking a look at the complex plane, we see the familiar Cartesian graph, but now the vertical axis represents the imaginary counterparts. The real part of z and the imaginary part of z should make more sense now. Setting y equal to 0, z rests on the real axis, and setting x equal to 0, z rests on the imaginary axis. The rules of vector manipulation apply to z, and one is able to ease more complicated calculations using polar coordinates. The first sighting of a negative under a square root was in the 1st century AD by Heron of Alexandria, a Greco-Egyptian mathematician and engineer often considered the greatest experimenter of antiquity. He was given a problem regarding the frustum of a pyramid with a square base, the problem later being presented in a work apparently written by him called Stereometria. His goal in the problem was to find the height of the frustum, but given the information for the calculation, he ended up with a subtraction that yielded a negative number under a square root. To avoid the negative, Heron simply...
Wow. Let me just check that the audio for this stream is working.
I equals the square root of negative 1.
Okay. So let's see. Volume of a frustum, 1/2 or 1/3 times height times a squared plus ab plus b squared. So I'll trust that's right. It's not the most important. I'll assume that's right. What we're trying to get at is the complex plane. Complex numbers, the square root of negative 1.
You swap the quantities in the subtraction to yield a positive under the root. An obvious arithmetic error showing that Heron most likely didn't even want to consider the notion of a negative under a square root. Around 200 years later, Diophantus of Alexandria, an Alexandrian mathematician most notable for his contributions to elementary algebra, also had an encounter with a negative under a square root. He showed this in his work Arithmetica, a series of 13 books containing a large quantity of problems along with their answers. A triangle problem in book 6 stated as, given a right triangle with area equal to 7 and perimeter equal to 12, find its sides, yielded a negative under a radical for both roots of the quadratic that came out of this information. Based on this, Diophantus stated that no equation actually existed since there existed no rational solution. It is unclear whether Diophantus just completely missed this or was just dumbfounded by the result. Over 1,000 years later, in the 16th century, Italian mathematicians began studying the depressed cubic, a cubic equation missing its square term. A depressed cubic always has at least one real root, and one can often encounter two complex roots depending on the equation. A few of the mathematicians involved in this cubic venture were Scipione del Ferro, an Italian mathematician who first discovered a method to solve such equations, Niccolò Fontana Tartaglia, an Italian mathematician, engineer, and surveyor notable for making the first Italian translations of Euclid's Elements, Girolamo Cardano, an Italian polymath who made fundamental contributions to the foundation of probability, and Bombelli, who we mentioned was the first to give a name to the square root of negative 1. The story begins with Del Ferro, who was the first to find a general solution to the depressed cubic equation. He made restrictions in his solution that only yielded a real root, and he mostly kept the solution to himself. The only people he told about the solution were a few close friends, and when laying on his deathbed, also told one of his students, Antonio Fior. Fior wasn't a very good mathematician, but given this rather exclusive formula, this allowed Fior to go on and win prize money from solving problems in computational contests. Fior's head, getting rather inflated from his wins, challenged Tartaglia to a computational match. Fior had discovered Tartaglia after Tartaglia announced he had found the solution to solving another form of a cubic, one missing its linear term instead of its squared term. Suspecting Fior got the depressive cubic equation from Del Ferro, Tartaglia dove headfirst into finding the solution for himself. Apparently, he discovered this the day before he was to face off with Fior, and to put it bluntly, absolutely destroyed Fior. Tartaglia's initial intention was to keep his solutions private, hoping to eventually publish them, though he never got around to it. Cardano was very intrigued by these solutions and begged Tartaglia to tell him. Tartaglia ultimately gave him the solution, but not the derivation, and Cardano swore to secrecy, intending to keep it that way, not knowing Del Ferro had solved this problem prior to Tartaglia. Once Cardano saw Del Ferro's surviving papers on this, he broke his vow of silence and published the formulas in his 1545 work, Ars Magna, giving both Del Ferro and Tartaglia credit. Though this didn't stop Tartaglia from feeling betrayed and accusing of plagiarism. Within the work, Cardano introduces the problem of dividing 10 into two parts whose product is 40. This led to a quadratic equation, x squared minus 10x plus 40, which yields two complex roots, expressing the problem as manifestly impossible. Nevertheless, he embarked on arithmetic manipulation of the roots. adding them together and multiplying them, yielding a real number in each case. He apparently said of this, "Putting aside the mental tortures involved, so progresses arithmetic subtlety, the end of which is as refined as it is useless," clearly showing how uncomfortable the negative under a square root made him. He was especially uncomfortable when these square roots ended up under cube roots when dealing with the depressed cubic equations, calling such an instance irreducible. In 1572, Bombelli wrote the work Algebra and addressed this occurrence using x to the third equal to 15x plus 4 as his example. This equation yields all real roots, x equals 4 and x equals negative 2 plus or minus the square root of 3. When using Cardano's formula, one ends up with the sum of complex conjugates, which ultimately sum to 4. Bombelli's brilliant insight led him to deal with a system of equations, setting each cube root equal to a plus ib and a minus ib respectively, where a and b are real numbers. From this deduction that each imaginary part would cancel out, and one would be left with only x equals 2a upon summing, this allowed him to focus on just the cube of a plus ib, ultimately yielding a equals 2, and thus x equals 4. This work was revolutionary, as it made it clear that one could toy with the square root of negative 1 with the usual rules of arithmetic. Published posthumously in 1615, a result of French mathematician François Viète, produced all the results of an irreducible cubic in terms of cosine and inverse cosine, avoiding complex numbers. In 1637, Descartes published La Géométrie. Within this work, he describes the geometric construction of square roots, the construction being for the square roots of any given line segment of positive length. He left out much of the work, commenting that he intentionally omitted so as to leave the others the pleasure of discovery. As mentioned earlier, even negative quantities themselves still seem to throw people off well into the 17th century. Descartes was no exception to this, looking at geometric constructions of negatives as making no physical sense and even ignoring them as roots to an equation. He went as far as to impose restrictions on certain equations so he would only yield positive roots. Otherwise, he would just ignore. Thus, the square root of a negative quantity wasn't going to make sense either, which of course led to him calling such quantities imaginary. John Wallis was essentially the first to embark on a proper geometric representation of the square root of negative 1. His first dealings began in 1675 when analyzing a triangle with sides 1 and 2 and a base of 4. But he only analyzed it with formal algebra as the triangle was actually impossible, yielding real solutions which seemed paradoxical. He didn't pursue the problem much more than that, but clearly his imaginary wheels were turning. Flash forward 10 years, he published Algebra in 1685, stating in the introduction that negative numbers were indeed able to be physically represented by going to the left of 0 in the Cartesian plane, with no issues at all, and later in the work producing his attempt at geometrically representing the square root of negative 1. He attempted two constructions, one using the mean proportional, which he was not satisfied with, and the other using two triangles that have two sides given, and an angle given that is not shared between the sides. This second attempt hinted at imaginary numbers acting vertically in a plane, though Wallis said nothing about this. It wasn't until Caspar Wessel that we were finally able to get the complex plane. Oddly enough, Wessel wasn't a professional mathematician. He was actually a surveyor, working hard to make the most efficient maps he could. It just so happened that a lot of the geometry he was working with was running into the imaginaries, so he needed some way to geometrically represent them. In 1797, Wessel wrote a paper with the help of the then president of the science wing at the Royal Danish Academy of Sciences, which discussed Wessel's research with the new plane he had created. The title of the paper was On the Analytic Representation of Direction, an Attempt. Wessel had a beautiful understanding of geometry, completely defining the complex plane as we know it today, yet he got no real acknowledgement for it in his time, as it was written only in Danish. Credit was finally given when the paper was rediscovered in 1895. Wessel began his paper by discussing vector manipulation. Instead of calling what he was manipulating a vector, Wessel simply called them line segments, first describing addition and then multiplication, where multiplication was Wessel's original contribution, since Wallis had expressed similar ideas regarding addition of line segments a century earlier. Not long after Vessel's paper was written, the complex plane popped up again, this time in France, because of a paper written by another mathematician, Jean-Robert Argand, who was also notable for providing the first rigorous proof of the fundamental theorem of algebra. In 1806, Argand wrote his paper on the complex plane in the form of a pamphlet under the title Essay on the Geometrical Interpretation of Imaginary Quantities. It wasn't until 1813, however, that Argand got recognition for this writing, which only came after a plea from the mathematician Jacques Francis, notable for his research in mechanics, land thrust in particular. He wrote his plea in Annales de Mathématiques, asking that the author of the essay come forward. Evidently, the mathematician Adrien-Marie Lejeune, notable for Lejeune polynomials and Lejeune transformation, found Argand's pamphlet and wrote a letter to Jacques' older brother, François Francis, a mathematician who worked extensively in differential calculus. But François died shortly after receiving the letter. While going through François' belongings after his death, Jacques found the letter discussing Argand's pamphlet, but Lejeune had failed to mention Argand's name in the letter, thus, the plea. Neither of the men knew of Vessel's paper on the complex plane written years before, and surprisingly, Vessel, who was still alive in 1813, never heard about Argand's pamphlet. In the same year Argand got recognition for his pamphlet, Augustin Cauchy, a French mathematician notable for his contributions to the foundations of mathematical analysis, developed his contribution to the theory of complex numbers. Cauchy submitted a memoir on complex integration to the French Academy of Sciences, and within his paper, introduced the contour integral, which is integration within the complex plane, and the idea of residue, which is to explain why the value of an iterated integral might be different, depending on the order in which the individual integrations are performed. Cauchy's work wasn't published until 1825, and the members of the Academy did not realize at the time that Cauchy was about to launch an entirely new branch of mathematics, that of complex function theory. For the rest of his life, Cauchy spent a great amount of his time developing the theory of the complex numbers, making it far more concrete. So concrete that by 1850, complex function theory was highly advanced. In 1828, yet another geometric representation of complex numbers arose after years of silence, though it was largely unnoticed. It was written by Reverend John Warren, a fellow of Jesus College at Cambridge University, titled A Treatise on the Geometrical Interpretation of the Square Roots of Negative Quantities, and his book was similar to the descriptions of Argand. In 1831, Gauss made his contribution to the theory of complex numbers, which included his geometric representation, finally making the geometry of complex numbers popular. As early as 1796, Gauss had already made a complex plane of his own, but felt the world was not ready for it to be published, thus waiting for it to ripen. In 1835, William Rowan Hamilton, an Irish mathematician notable for his important contributions to optics, classical mechanics, and algebra, produced his own work regarding complex numbers that focused only on the algebra. It was titled Theory of Conjugate Functions or Algebraic Couples, with a preliminary essay on algebra as a science of pure time. Hamilton had read Warren's book a year after its publication and was in disagreement with Warren's presentation. He felt that complex numbers should stay purely algebraic, that algebra, with its square root of -1, was separate and distinct from geometry. In his paper, ordered pairs of real numbers were introduced as couples for the complex plane. He also defined addition and multiplication of these couples, making the numbers less confusing and more believable, as people were still having trouble accepting the idea of imaginaries. For the years up until his death, Hamilton, just like Cauchy, contributed a great portion of his time to the algebra of complex numbers. As one can see, the conception of the complex plane was no easy feat. What we are so accustomed to today was quite a foreign idea to many until just recently. Beginning with Heron of Alexandria in the 1st century AD, the lack of acceptance for square root of -1 continued even through the 17th century. But it is from there that the magic happened, and the path to the complex plane unfolded rapidly, developing into the concrete fundamental tool we use today. If you enjoyed the video, please click that like button and subscribe. And if you generally just enjoy the content of this channel, please consider supporting on Patreon. As always, thank you for watching, and I'll catch you next time. And if you generally just enjoy the content of the video, we use today and through this first day with the examples, making the numbers less confusing and more believable.
So I think here is where some practice can be done. I've heard adding complex numbers is simple. You just add the x and the y coordinates, but multiplying is more complicated than you think, because let's see what's happening here. X1. Yeah. How do I illustrate this? So multiplying is a little more complicated. It's, let's see, z1 equals x1 plus y1 I. So 2 equals x2 plus y2 I. You do z1 times z2. You're going to use FOIL, first, outer, inner, last. So let me just make that a little more clear. So the first, outer, inner, last, so that last term becomes just a -1 here, so you basically have this. And -1, and this is y1, y2. So what this is, just in the coordinate system, it's just the real part and then the imaginary part or coefficient. So without cheating and looking, let me just go expand this. You're going to have x1, x2, that's real, minus y1, y2. This is the real part. And then imaginary part is this right? Is this? Yep. It looks. Oh wait, it looks promising, but I just messed up that part. This is a plus. X1, y2, I plus y, x2, y1. I. Yeah. This it becomes this x1, x2 minus y1, y2, comma. And this is the imaginary parts with the I, x1. I wonder what's the best way to put the order of the x1 and y1. So it's, yeah, just do it, x1, y2 plus y, x2, y1. Yeah. So this agrees with what's on the YouTube video. Alright, I think that's a good exercise. And what I heard is that, I think there was a picture of it too, so we can practice that part. Basically, what was that? I saw. Yeah, this part. So basically, when you add, it's very simple geometric intuition, geometric interpretation. You add, you know, this complex number to this complex number, right? A plus B, and then this is the new complex number you get in the complex plane. But when you multiply, it's a little more complicated than you would think, than I would think. This is showing what is being multiplied. Okay, the AB, so 3 plus 3i. Wait, the red is the second. So the red, what is, what, okay, negative 1 plus 4i. Just put this example 1. Maybe 1 plus 4i times 3 plus 3i, this equal 2. Is this what they're doing? Or is it the other? Minus 4i. End up with 3. So what is the order of operations? End up with 3. So basically it's an interpretation geometrically of you. If you want to multiply these two complex numbers, it's going here. Yeah, it's kind of weird. It's just, then you point it in the opposite direction and you get that. I think that's what it's showing. So let's work this out. This would be negative 3 minus 3i plus 7i, oh shit, 12i plus 12 times negative 1. It's going to be right, huh? That's getting to negative 15. No, I don't think this is right. They're showing a different one. What is negative 1 plus 4i times negative 4 plus I? That is 4 minus I minus 16i plus 4 times negative 1. I mean, that's negative Oh shit, that's like negative 79. Okay, so that's not that one. Do this one, this one. Gosh, I don't even know if this is commutative. Is this commutative? Either. Am I doing this wrong? I think I just wait, this might still be adding. Probably still adding this. Okay. I think I jumped the gun. I think that they're still adding it. None of these numbers are working out. Plus 3i. Yeah, because it's making the same kind of parallelogram. Okay. I know I saw another YouTube video in which it was talking about how the multiplication of complex numbers is a little, you could say it's just a tad, a little, a bit, or significantly more complicated than you think. I think they're just adding this. Let's see here. 3 plus 3i. Where are they? Oh no. Oh no. What are they explaining here?
Not long after Vessel's paper was written, the complex plane popped up again, this time in France, because of a paper written by another mathematician, Jean-Robert Argand. This set of multivector, his paper by discussing vector in 1895. Vessel began his paper by discussing vector manipulation. Instead of calling what he was manipulating a vector, Vessel simply called them line segments, first describing addition and then multiplication, where multiplication was Vessel's original contribution, since Wallace had expressed similar ideas regarding addition of line segments a century earlier. Not long after Vessel's paper was written, the complex plane popped up again.
So yeah, this is multiplication, but what the heck are they multiplying? How the heck are they doing it? I mean, gosh. Adding vectors is really add. That's the added. Multiplying vectors is this, or this. Well, no, this thing is also 9i, right? It's easy to do some mistakes. Right, so the next one. It's not what. This would be an awesome use of Python, which has C math, complex math library, and let's see, complex 3 multiplied by complex -1 4. Yeah, 15 plus 9i, that's right. What permutation is they doing to get, they're showing what? So at least we have established this is commutative. You can change the order to the same answer. Alright, they're not, maybe we're not supposed to take this literally, maybe they're trying to show something else. None of these numbers work out. Anyway, thought it was somewhere on YouTube. Graphically. This is pre-calculus? Okay. Back to high school here.
We are told, suppose we multiply a complex number z by -1 minus I. So this is z right over here. Which point represents the product of z and -1 minus I? Pause this video and see if you can figure that out. Alright, now let's work through this together. So the way I think about this is when you multiply by a complex number, you are going to rotate by the argument of that complex number, and you're going to scale the modulus of z by the modulus of this complex number. Now let me just think about that a little bit. So I'm going to draw another complex plane here. And so this is my real axis, This is my imaginary axis right over here. And -1 minus I, so that's -1, and then minus 1I, so it would go right over there. It would be that right over here. And so let's think about two things. Let's think about what its argument is, and let's think about what its modulus is. So its argument is going to be this angle right over here. And you might already recognize that if this has a length of 1, if this has a length of 1, or another way of thinking about this has a length of 1, this is a 45, 45, 90 triangle. So this is 45 degrees, but then of course you have this 180 before that. So that's going to be 180 plus 45 is a 225 degree argument. So the argument here is going to be equal to 225 degrees. So when you multiply by this, you are going to rotate by 225 degrees. So let's see, this is going to be rotating by 180 degrees and then another 45. So if you just rotated by that, you would end up right over here. Now we also are going to scale the modulus, and you can see two choices that scale that modulus. And so we know it's going to be choice A or choice B, because choices C or D, you'd have to rotate more to get over there. And so to think about that, we have to just think about the modulus of -1 minus I, this point right over here, and then just scale up Z's modulus by that same amount. Well, the modulus is just the distance from 0 in the complex plane, so it's going to be this distance right over here. And you could use the Pythagorean theorem to know that this squared, if you call this C squared is equal to 1 squared plus 1 squared, or C squared is equal to 2, or C is equal to the square root of 2. So that's the modulus right over here. Modulus is equal to square root of 2, which is approximately, it's a little bit more than 1.4. So let's just call it approximately 1.4. So not only are we going to rotate by 225 degrees, we're going to scale the modulus, the distance from the origin, by 1.4. So if it looks like it's 3 units from the origin right over here. If you multiply that by 1.4, 3 times 1.4 is about 4, or it is exactly 4.2. So 4.2 of these units is 1, 2, 3, 4, and a little bit further, you get right over here to choice B. And we're done.
Okay, so yeah, that's what I saw. I don't know. Okay. I saw a similar explanation, so I'm glad it's easy to find. And basically, basically they, I don't know how they.
Geometrically, paper was written, the complex plane.
So this thing here, multiply this by this, it means you rotate this by that, and then you scale it up by the absolute value. Yeah. So it's a two-step thing. You rotate by the argument, as they call it, the terminology argument, and then you scale it by the modulus, or another term for absolute value. So Well, yeah, it's a two-step geometric interpretation, which is a little more complicated than I would think it is as well. Yeah, just remember it's a two-step. It's a two-step geometric intuition, two-step geometric interpretation. This is, I put in every permutation of this example and it did not get what I would expect at all. It's not anything like this. Maybe they're just saying maybe it's not exactly showing this multiplication very correctly. I literally put in every single way. Alright, I think it's enough for this one. I got other stuff to do. Hope that was good practice. I know it is for me. I'm remembering this more deeply, what it means to multiply complex numbers, and I'm going to go through more videos hopefully as I have time to do so.